So we've been looking at these graphs of force versus time. Again, this is showing how what a real force looks like, where a real force kind of, starts at 0 and increases to some maximum value and then decreases. This would be like, if you're hitting a bat with a baseball, this is what the force really looks like. And we've said that the area underneath here demonstrates the capability of this force to change an object's momentum. So let's give a word for that. Let's, instead of having to always say, how much can this force change an object's momentum, we're going to use a new term to describe that, and that's called impulse. So impulse is the capability of a force to change the momentum of an object. So it's a way to kind of look at how big is the force and how long is the force acting on our object. I'm not going to be able to say how the velocity of our object will change because I don't know what the mass is. But this area underneath here tells us how the momentum of the object will change. So we can define impulse in this way. We're going to use a big capital J to represent impulse. And impulse is equal to the integral of F dt. So this is a force that's changing in time. And if I had F as a function of time, I could integrate it with respect to time. But really we don't do it that often in this class. More often what we do is we look at a graph. In this case, we'd be looking at a graph of force as a function of time. And in that case, the integral of that graph represents the area underneath the force as a function of time graph. So this area here is my impulse. The units we're going to use for impulse are kilograms meters per second. So for force, our units are newtons, which are kilograms meters per second squared. And then the units here is just seconds. So we'd have kilograms meters per second squared times seconds. That gives us kilograms meters per second. That looks familiar, and that's not a coincidence that that looks familiar. Those are also the units for momentum, but we'll see that in a second. Now, if you're looking at a graph for some force that has some weird shape like this, it will be hard to calculate the area of this shape. So instead, what we're going to do most of the time is we're going to be told what the average force is. And if you know your average force, then you can replace this weirdly shaped graph with a nice rectangle where the area underneath this rectangle is the same as the area underneath this shape as long as the average force is correct. Okay. So now to calculate the area of this rectangle, that's very easy. The height of the rectangle is F average, and the width of this rectangle is just the duration of the force, or how long the two objects are in contact, or just delta t. So another way to calculate our impulse is to figure out what is the average force acting on our object, and how long, how many seconds is that force acting on our object. This delta t is the duration of the force. This is the amount of time that the object is experiencing that force, or in the case of like a golf club hitting a golf ball, this delta t would be the amount of time that those two things are in contact, because that's the only time that there's a force being exerted on the golf ball. So now that we have our definition of impulse, and here is I'm just showing you two different ways to calculate impulse. One is if you know what the average force is and how long it's acting on our object. Here is if you're either given a graph of force versus time, or if you know the force as a function of time. These are just the two different ways to figure out impulse. The impulse momentum theorem tells us that the impulse given to an object by a force is going to be equal to the change in the momentum of an object. So we've already kind of said that. We've already introduced this idea when we looked at a graph of force versus time, and we said that the area underneath that graph is equal to the change in the momentum of an object. But now we're just kind of saying it formally. So a good way to think about what this theorem means and how we can use it is to rearrange things a little bit. Instead of writing this as delta p, if I write this as p final minus p initial, and then I rearrange it with the j, I can write it as p initial plus j equals p final. And this is kind of saying that an object starts with some initial momentum, and then the object receives an impulse from a force. So there's a force, it gives an impulse. What is impulse? Impulse is the thing that changes the object's momentum. And as a result of that impulse, now the object has a different final momentum. And then we can say, well, how do we calculate impulse? That's just the average force times the time that the force is acting on our object. So this equation here is the impulse momentum theorem. This equation here kind of helps you make sense of what impulse is and what it does. And you might notice that this impulse momentum theorem looks a lot like the work energy theorem. The work energy theorem said net work is equal to delta K. And net work was equal to your net force times the distance that force was acting. So these two equations, the impulse momentum theorem and the work energy theorem, they are describing the exact same thing. They're just using slightly different variables. With the work energy theorem, we cared about how big the force was and what's the distance that the force acted over. Now we're looking at how big the force is and how long in terms of seconds that it's taking for that force to act. And this value shows us the change in the momentum of an object, whereas the net work done shows us the change in the kinetic energy of our object. Both momentum and kinetic energy depend on the speed. So when it comes down to which equation are you going to use, it just depends on what you're being given. Okay, and we'll go through some examples where we use the impulse momentum theorem.